The paper of the day is No Compromises: Distributed Transactions with Consistency, Availability, and Performance. Transactions with strong consistency and high availability simplify building and reasoning about distributed systems. However, previous implementations perform poorly. This forced system designers to avoid transactions completely, to weaken consistency guarantees, or to provide single machine transactions that require programmers to partition their data. In this paper, they show that there is no need to compromise in modern data centers. Papers show that a main-memory distributed computing platform called FARM can provide distributed transactions with strict serializability, high performance, durability, and high availability. FARM achieves a peak performance of 140 million TTP transactions per second on 90 machines with a 4.9 terabyte database, and it recovers from a failure in less than 50 milliseconds. Key to achieving these results was the design of a new transaction replication and recovery protocols from first principles to leverage commodity networks with RDMA and a new inexpensive approach to providing non-volatile DRAM. Paper uses two transactional benchmarks to measure FARM performance. They implemented both benchmarks in C++ against the FARM API. Since FARM uses a symmetric model to exploit locality, each machine both runs the benchmark code and stores data. Telecommunication application transaction processing, that is TATP, is a benchmark for high-performance main-memory databases. TPCC is a well-known database benchmark with complex transactions that access hundreds of rows. Paper experimentally shows that you can have it all: consistency, high performance, and performance. Consistency, high availability, and performance. FARM recovers from single machine failures in less than 50 milliseconds, and it outperforms state-of-the-art single machine in-memory transaction system with just a few machines. For example, it achieves better throughput than Hackathon when running on 3 machines, and it has both better throughput and latency than Silo. Let's look at some FAQs. Does FARM really signal the end of necessary compromises in consistency availability in distributed systems? I think we suspect not. For example, if you're willing to do non-transactional one-sided RDMA reads and writes, you can do them about 5 times as fast as FARM can do full transactions. Perhaps few people want their 5 times more performance today, but they may someday. Along other dimensions, there is a good deal of interest in transactions for geographically distributed data, for which FARM doesn't really seem relevant. This paper does not really focus on negatives of FARM. What are the biggest limitations of FARM? There are some guesses. The data has to fit in RAM. OCC will produce lots of aborts if transaction conflict a lot. The transactions API looks awkward to use because replies return in callbacks. Applications code has to fight or to tightly interleave execution application transactions and polling RDMA NIC queues and logs for messages from other computers. What is RDMA and one-sided RDMA? RDMA is a special feature implemented in some modern NICs. The NIC looks for special command packets that arrive over the network and executes the command itself and does not give the packets to the CPU. The commands specify memory operations such as write a value to an address or read from an address and send the value back over the network. In addition, RDMA NICs allow application code to directly talk to the NIC hardware to send the special RDMA commands packets and to be notified when the hardware ACK packet arrives, indicating that the receiving NIC has executed the command. One-sided refers to a situation where application code in one computer uses these RDMA NICs to directly read or write memory to another computer without involving another computer's CPU. FARM's validate phase in section 4 and figure 4 uses only one-sided RDMA read. FARM sometimes uses RDMA as a fast way to implement an RPC-like scheme to talk to software running on the receiving computer. The sender uses RDMA to write the request messages to an area of memory that receiver's FARM software is polling, that is checking periodically. The receiver sends his reply in the same way. The FARM lock phases uses RDMA in this way. The benefit of RDMA is speed. A one-sided RDMA read or writes takes as little as 1/18th of a microsecond, while a traditional RPC might take 10 microseconds. Even FARM use of RDMA for messaging is a lot faster than traditional RPC. User space code in the receiver frequently pulls the incoming NIC queues in order to see new messages quickly rather than involving interrupts and user kernel transitions. Why is FARM's RDMA-based RPC faster than traditional RPC? Traditional RPC requires the application to make a system call to the local kernel, which asks the local NIC to send a packet. At the receiving computer, the NIC writes the packet to a queue in memory and interrupts the receiving computer's kernel. The kernel copies the packet to the user space and causes the application to see it. The receiving application does the reverse to send the reply. This point is that a huge amount of code is executed for each RPC and it's not very fast. Much of FARM's performance comes from the hardware. In what way does the software design contribute to performance? It's true that one reason farm is fast is that the hardware is fast. But the hardware has been around for many years now, yet no one has figured out how to pull all the parts together in a way that really exploits the hardware's potential. One reason farm does so well is that they simultaneously put a lot of effort into optimizing the network, the persistent storage, and the use of CPU. Many previous systems have optimized one, but not the all. A specific design point is that the way farm uses fast one-sided RDMA for many of the interactions. Would farm make sense at small scale? I think farm is only interesting if you need to support a huge number of transactions per second. If you only need a few thousand transactions per second, you can use off-the-shelf mature technology like MySQL. You can probably set up a considerable smaller farm system than the author's 90 machine system. But farm doesn't make sense unless you are sharing and replicating data, which means you need at least 4 data servers, two server per shards, plus a few machines for Zookeeper, though you probably could run Zookeeper on the 4 machines. What is vertical Paxos? It is a style of Paxos protocol where an external master performs reconfiguration while the Paxos group can continue performing operations while reconfiguration is in progress. In the farm paper, the authors use the term vertical Paxos loosely to mean that the reconfiguration management is done by an external service, most likely Zookeeper or CM, and processing rights of transactions is done with standard primary protocol.